call? That would
It's
be
a differential.
a differential.
Usually there's a differential adjustment on
Now,
a.
my well, the differential adjustment, I can't physically see, but what I can do is I can turn the hose open and I can see when it comes on, and then I can see when it stops. And I can adjust it with like a quarter, I think it was a quarter drive or 3/8 inch drive. And then I can see, okay, it starts sooner or later, and I can change that range.
Yeah, you're kind of adjusting the tension on that spring, probably, I think is what you're doing.
Got it. All right, we'll move on. Next one is going to be some common applications: air compressors, well pumps, man, hydraulic systems. There's just unlimited number of applications for pressure switches. A vacuum switch, another type of pressure switch. Instead of pressure, there's a vacuum chamber. Some vacuum switches are manufactured. They can serve either function. A vacuum. How would that work? Is that where it goes the opposite direction, right? So if the pressure goes down, how does the vacuum work? Oh, this is a vacuum chamber. Anybody have any experience with vacuum at all? Dan? Tell us about vacuum.
The diaphragm would pull down, and your normally closed contacts would actually open.
Okay, so what it's going to do is it's going to go down where if it's going to be pressure, where it's going to be going up where the vacuum is. Okay, it's going in the opposite direction. Pressure is going in that direction. Okay.
Yeah, normally they're a large diaphragm. You have a fitting on either side of the diaphragm, so that normally can either be used for vacuum or for pressure. Or if you connect both lines, they can do differential pressure, which you might need, like if you were wanting to know when your air conditioner filter was dirty, you could put one on either side of it and have a setting to where when your air conditioner filter was dirty,
when it
would
got too much pressure, the differential.
Turn on a light, yes.
Excellent. Let's take a look at the symbol. So this is a vacuum. What's the difference between that and a pressure? Okay, so there's no difference you'd have to know the application. All right, let's move on. The setting of the spring, which Steve, I think you mentioned it, determines what pressure the electrical contacts change state. There's often a setting to adjust the differential between the switching points. Push buttons. Push buttons, they're switches that are pushed to make or break contact rather than move a handle. Now, be aware that this is your momentary contacts normally open, right here, here's the symbol. And then we have normally contacts that are normally closed, momentary contacts that are normally closed. And Dennis, you got a couple switches there, and let's take a look at those. Let me see, are they red and
One's
green?
red and one's green.
Now, both of those red and green, are they both identical switches in the sense that they're normally open, normally closed, and that red is just something?
Yeah, this comes out, this pops out right here. It's just a little disc.
Okay.
And that just pops out.
Do you have some of these that are illuminated under normal conditions?
Yes, you could have some of these that are.
So that'd be a
illuminated,
separate little power for that there.
And then typically they're going to come with, one's going to be normally
Let's
open.
see if we can
the
zoom
other
in a
one's
little
gonna be
closer on that.
normally closed.
Okay.
Okay. And all it's got in there is a spring. And so when you push it down, it just goes the opposite direction.
Okay, that's a momentary, normally closed, a momentary close and a momentary open.
Right. Right now it's in the de-energized state.
Right.
So when I push it, the normally open goes closed and the normally closed goes open.
Got it. All right, we'll move on. Pretty simple, straightforward. Push buttons. A single push button switch can have additional sets of momentary contacts. Let's take a look at this. And that's what we just showed, what you just explained, Dennis. Normally close, when you push it, will go to open, and then the normally open would end up going to close. Or the symbol could be just simply like this here, showing you a momentary push button. There's a set of normally closed contacts and a set of normally open contacts. Now, we've been showing the NC, NO, and we haven't described it, but I think people have picked it up, normally closed and normally open. In reality, on the diagrams, do they tell you that it's normally open or normally closed? Or when you look at the diagram, you can see it's a de-energized state, and you can see that this is already closed, and this is already open, so that means this is a normally closed button, and this is already normally open. Is that the way it's shown?
That's correct.
Okay. And here, Dennis, looking at your switch, does it tell you which one is, does it show you a symbol of the normally open, normally closed, or does it tell you that's normally closed, normally open? How do you know on the 4 screws?
Well, it's got the normally Closed is up on top here.
It shows a symbol of it?
Yeah, it shows the symbol with the regular contact, and then it's just got a slash line through it, so it's normally closed.
Got it. There are many other push button configurations. Some have larger mushroom heads and are illuminated buttons. So here's a symbol of a mushroom head. This is normally open, momentary close. Normally close, momentary open. And then you get illuminated. And you press the illuminated button, and we'll talk about that. But that's normally closed, momentary open, normally open, momentary close. And Steve, I think you got a...
Yeah, I've got one with a mushroom head on it. And those heads, this particular one comes with either the mushroom or just a standard head, and you just interchange them with an Allen wrench.
I was just going to say, how do you get... So you just
Yeah,
get a
there's-
regular...
there's
the
an
one that
Allen
Dennis
screw.
had showed us, you just would get the mushroom head, you just kind of get it on there.
Well, it came with the switch, but the switch is just versatile where you could use it either with or without this mushroom head. I can just take these screws out. Back
Now, you
off
know,
a
the
little
National
bit,
Code sometimes,
and you can change the heads on that one. It just got
different
set
colors,
screws.
different configurations.
Yeah, and a lot of these others, here's another one that comes with different heads, different color heads. So you can use them or you can use the red head, depending if you're using it for a stop or a start.
Got it. All right, let's go on. Continue on push buttons here. This is a push button station. It's an enclosure that contains a combination of push buttons. You know, whatever. And of course, you can get legends and you can get, plates and marked and, engraved and whatever else you want there. What do you got there, Steve? What's that
I've
one?
got one here that is just one button, one situation. It has both buttons, both a start and a stop in the same,
Okay,
in
there's
the
your
same
station right there.
device. Like
Okay. Solenoid. Let's talk about some solenoids. It's an electromagnetic with a movable plunger. When the coil is energized, the magnetic field pulls the plunger in. We talked about this a little earlier, and when it's de-energized, the plunger then moves back to its original position. All right, here is a solenoid symbol. Right now it's de-energized. If I energize it, it's going to pull the plunger in. Here's an example of a solenoid. This is often used for sprinklers that, you run your 2-wire control wire here, like in my house has sprinklers. Well, then you run 2 wires to this solenoid. You energize the coil. That magnetic field draws in this armature or this plunger, and the result is that it opens up the water flow, and they continue on, and liquids move for whatever the process that you want to move for. Toggle switches. Manually operated devices. Kind of straightforward. Just turn a switch on. Well, what does that look like? Well, it has a switch like this. Now, we're going to talk about these abbreviations, which was discussed in the abbreviations unit. I think that was unit 2 that we didn't talk about. And this would be a single pole, which means there's only one line, and it's single throw, meaning you either open it or you close it. So your switch at your house that you turn on your lights is going to be a single pole switch because it doesn't have, it's not 240, it's just 110 in this case. And it either goes on or it's off. So it's single pole, single throw. Okay, got that one. Here is a single pole, meaning, one hot wire. Double throw, which means you could have it on load B, or you could switch it and go to load A. It's double throw. It can go one of 2 directions. Eric?
Also, it's very typical for that contact to be described as a Form C contact.
Form C.
Form C. A Form A contact is a normally open, like you showed on the previous slide. That would be considered a Form A. And on lots of literature, you won't see NO, you'll see A. You'll have an A contact. And
Well,
a
I don't know where the A came from, but I can see where that could be looking like an A, right? And I can see where this looks like I can see this looks like a C. I can visualize how this looks like a C. So at least there's a little bit of logic if that is the logic.
Well, to continue, Mike Colbreth has gotten some of his graphics and some of his limit switches and things. He'll have a normally open and then a normally closed.
Right.
Okay, well, a normally open is a Form A, a normally closed is a Form B.
Oh.
But sometimes when the normally open and the normally closed are together with the same armature, then it's a Form C.
Okay. All right, let's look back here. This is a three-way switch, right?
Right.
Single pole, double throw. So it's a three-way switch where you can go from this point here, you can supply load B, or switch it up and supply load A. I don't want to get any more detail, I think, right now on that. But I guess I am. This is a three-way switch, which is a single pole, double throw. Let's go back here. Single pole, one line, and it can go up and down, so it's double throw, SP, DT. And if you put a single pole, double throw on the power coming in, and then you put a single pole, double throw supplying to the load, you can use two three-ways. And by the way, single pole, double throw is a three-way switch that you can control one load from two different locations. Let's take a look at this. Line one comes in. The switch, in this case, is closed at this point. Power goes over here and it stops. The load is not operating. Take the first switch and go to the other position, the other throw, up. So now it takes power, goes up to the top portion of the first three-way. Then it goes over to that three-way that was already in that position, supplies a load. So that means you can turn the load on and off by going to switch one, three-way. Now, back to our state again. If I take that switch on switch one, leave it where it was, which was on, or it was up, go to switch two and turn that switch the opposite direction, the load goes off. Then I could go back to switch one, since it was already in the up position. I could switch it down. It would then turn the load on. Eric?
It might be beneficial to note that in a single pole double throw, the double throw refers to the number of on positions.
Hold on, slow this down. The double throw refers to the number of on. I love it. The way you think, Eric, is always brilliant and it's fascinating to me. The number of on positions.
Right,
Double
because-
throw. You could throw it on here. Okay, I got it.
Because you also have a single pole double throw center off. You either have a switch which is on, or you have a middle position of off, and you can go either way.
And that would be called single pole, double throw. Well,
Center off.
Center off. Okay. Let's go on the next one. We're now moving to continuing symbols for switches. We're just talking about symbols, not how the stuff works necessarily. This is going to be double pole. That means, here we go, line one, line two, and then we're supplying the load one, load two, double pole, and it's a single throw, and that's a number of on, and there's only one on, so it's a single throw. Got it? Here's a double pole, double throw. So I have two poles, line one and line two. I have the on up, and it's a double throw because I can throw it down. Now that's one method, double pole, double throw, single break. Then you could have a double pole, double throw, but it's double break, where I'd press 1 and 2 would be contact, and 5 and 6 is contact, but if I press the button, this shows a mechanical connection, that if I press this button here down, it opens 1 and 2, closes 3 and 4, it opens 5 and 6 mechanically, and it closes 7 and 8. Help me, guys. Why would I use one versus the other? Is there a reason to have a double break versus a single break?
Well, one reason, Mike, to have a double break contact is for higher current flows. If you just have a single break, then your current has to be broken on a single contact.
Hold on. If I have a single break up here, you're saying when I push this button, I'm breaking all the energy on a single
Right.
point, and I'm making then, if we show the next symbol, I'm making it all in one point.
Right.
But if I do a double break, the contacts are going to be open at two locations. The energy of the arcing is going to be at two locations. And when I make the contact on 3 and 4 in this example here, then I'm distributing that arcing, that making the contact at two locations.
Right.
Really? Well, would this then have to do with the rating of the switch? I
Yes.
mean, so if I buy a switch that's a single break, it rates so many amps. But then if I buy a double break, it rates more amps. Right? It's rated for a higher ampere rating.
Right.
Dan, you're giving me I don't know about that whole story there, Mike.
Well, why
think-
we normally use them, if you have a double pole, double throw, would be so that you can separate the two circuits more than, so that you would have a normally open and then you could use the normally closed in another location in the circuit.
Okay, what you're saying is that this allows me to have two separate circuits.
Yes,
That I want this one to open, which is a separate circuit to open, and I want this circuit to close, and they might be off of different power supplies, maybe different even anything.
like when you were talked earlier about the limit switches, if you had a limit switch to change direction, like on a knife grinder that would go back and forth, sharpening the knife on a grinding wheel, that your limit switch could break one circuit to cause the travel in one direction to stop, and then also start it in the other direction.
Okay, so there might be different applications.
Yeah,
So there might be ampere ratings. Hey, listen, I don't want to have just one circuit controlling up or down. I want to have maybe two different things, one to close in this case and then to open this case. Okay, gives you more devices in, or more control or more make and break contacts in the single device. Steve?
Yeah, then if you're going to use your symbol in B up here, in the same way that you use A, you're going to have to put in a jumper between 1 and 3 and between 5 and 7 to make it actually duplicate that.
You're saying, Mike, if you want to have one come in and make it a double throw, then you would put a jumper between 1
And 3
and 3.
and between 5 and 7.
Let's see, a jumper 1 to 3?
Yeah.
And a jumper two. Oh, I see what you're saying. Yeah, but then the numbers aren't related here. You're just
Right.
basically saying these are connected to 1,
Yeah.
right? And you can normally close, normally open.
Right.
And 5 and 7, you can jumper it. So you can get this effect
Yeah.
by putting a jumper across these.
Right.
You know what I'm picking up here? Is that once you learn how this stuff works and how it kind of connects, you really have to be knowledgeable in product. You got to know what is available. Because you're saying, I want to achieve this. Well, in order to achieve that, then you have to understand that they must make devices that are proximity switches with inductions or capacitance or optic or that it makes this break this one. So you design what you want, then you're going to have to go out and find somebody that makes those type of devices, right?
Well, and the other thing about that also is the fact that all of a sudden you may have to be troubleshooting something. And like we were talking yesterday, Eric and myself, was that, you know, on a plant, if it goes down, it could be $1 million a day downtime. So just because of one little part like that, you need to understand how that thing functions so that you can replace something that broke so you can get something back up online.
Like Steve said, you can rewire this, put a jumper here, in other words, something,
Exactly.
because you know how it works. Now, Eric, at lunchtime, you were saying that some of these switches don't necessarily make it real clear exactly how it works, and that you'd have to get a continuity tester.
Yes, Mike, on the back of this switch, which is not made in the United States, but regardless, you have 4 different symbols, 2 normally open, 2 normally closed, and by looking at the back, it's not necessarily obvious which one goes to which. Looking at the side, it becomes a little bit more apparent, but you can't, there's no plexiglass, you can't see the contacts, and so sometimes, even if you've been in the business for quite a while, it can take it can take a bit of looking and analyzing just to see which contact is which.
You might have to get an ohm meter, just say, oh, okay, here's the close, here's the open.
Right.
And not, okay. Thank you. All right, let's go on to the double pole, double throw. And the double pole, double throw would be what we would call in the field a 4-way switch, where in one setting, it would go from this point to this point, and then if you switch it, the double pole, double throw, this one then switches down and switches up. I'm not going to get into too much of this, but let's just describe this. Here's your 3-way switch in the beginning. Here's your 3-way switch at the end. Here's your 4-way switch in between. Right now, this switch setting, the way it's set, there is no power to that given load. All I have to do is take any one of these three switches, either the three-way, the four-way, or the other three-way, and change the switching. In this case here, we're switching the double pole, double throw. That changes, the power goes in, goes up, over, and supplies the load. Dennis.
Mike, I think at this time, I mean, if you look at this, you know, the typical residential wireman, even a commercial wireman is looking at this and going, you know, now this is really starting to make sense because for the simple reason, you know, the load is a light bulb.
Right.
And now we're taking it back to the basics and saying, this is all it's about is motor controls is you can use switches for motor controls. So to me, this really helps, you know, a typical
if
person.
all our switching done was mechanical, you close this one, and then you open this one, and you open this one, you close this one. I mean, if it was all done mechanical, then the guys wouldn't have any problem following
Right.
that. You'd have all these switches all over the place. Okay, close this one, okay, and open this. But the problem is it's put in these in containers, and it's done electronically, and then it's into computers and programmable logic controllers that it's to get further and further away, that you got to be able to visualize this and have that concept of what is really happening out there. All right, let's move on to a non-fusible disconnect, also called a safety switch. This type of switch can be used as a manual on-off disconnect and incorporates the use of pivoting knife blade type contact points that operate from a handle. Just your regular standard old disconnect. And here's your symbols: double pole, single throw. This is three pole, ABC, line 1, 2, 3, single throw. And this shows that they're mechanically connected together. That's your handle, which is right there. Those are your blades, making contacts right here. And so what's three phase, a single phase, three phase, doesn't matter. Here's the symbol. Fusible disconnect, kind of like a no-brainer. The difference is you just add fuses to the disconnect. There's your knife blades. There are your fuses. Single pole or single phase and three phase. Temperature switch. This type of switch has a sensing bulb with a capillary tube connecting it to a chemically filled bellow. Eric, you know all about words. Is that supposed to be a bellow or bellows?
Bellows.
Why? Oh, no, I'm not going to go there. Fine. So here is a temperature switch. Let's see how this works out now. This is a sensing bulb. And I guess it will then let us know. And then we take, now could this be used, I guess it could be on-off, a regular thermostat, right? However it's going to work. We could probably show a picture of a thermostat in there also. It's a, might not have a, well, wouldn't have a capillary tube, but I mean, it could just be a make and break based upon a bimetal. Here is a symbol. Do you guys have much experience with temperature sensing? Do you guys, Dan, you guys use any of that at all? Is that?
Yeah, we use a lot of temperature sensing.
Are you sensing a specific degree that you can put in a computer and it says what the temperature is in that particular location? Or are you saying when it gets to a certain temperature, then start a process or end the process? Or what's the applications that you use it at?
Normally, these type you would use to sense either something's too hot or something's too cold. A lot of our control, of course, is analog, which means that we sense a variable temperature and can control based on that.
So
But
you would know
to
what the
be on,
temperature.
off.
So with a computer tying in your equipment, you would know what the temperature actually is at that given point. And then based upon that information, you could take action.
Yes.
Eric, what about you guys on Dow Chemical?
Same thing. We have analog measurements to where we will, a temperature element, for example, will be a RTD, which goes to a transmitter. It's all electronic, in other words, instead of the mechanical bellows and the contact switch, but the principle's identical.
All right, let's move on. Timing relay. Pneumatic. When the relay is energized, the solenoid plunger is pulled up, air enters through a needle valve, and slowly fills the bellows. When the bellow air chamber is filled, one or more sets of contacts are activated. Modern timers are usually solid state. All right, let's take a look at this one here. So this looks like it had to be like old school stuff, that you put a coil, you energize this coil, and it starts to try to do something with the armature, and of course there's air in there, and then, you know, we have a valve in there that allows the air to kind of slowly leak out, and as the air displaces itself, then it can then make and break the contacts. So it's a timing device, and so here's your adjustment as to say, well, how much air are we letting allow to release determines how fast that contact is going to close or open in that case. Is that like old school? Do we still use this, or is it more done electronically? That is a electronic timing device. You got something?
Nowadays, normally you use electronic timer. Those were real popular because you could use an off delay, which is
Yeah.
hard to do. You used to have to use 2 delays to keep something on after you've turned it off for a short period of time. The problem with those, especially in a mill condition, is you have a lot of dust and you actually have a spring in the bellows pushing against a needle valve, and very, very precise. Well, you get a little dust in there and you're not precise anymore, so the timing could vary considerably.
Steve, show us the one that you have your timing relay. Now, what are the choices, Steve, on that timing relay? What were the choices that you had? I see there's some adjustments.
Yeah, there's adjustments. This one has both an on delay and an off delay, so you've got both those incorporated in the same timer. And then you've got the amount of on time you can adjust, the amount of off time. And then there's a selection of ranges. You can change the range so it'll time anywhere from 0.6 seconds up to 24 hours.
So that's pretty cool. I like that. And here's the symbol right there. Here's a normally open time close. Normally close time open. And the energized arrow is on time delay. Down arrow is on delay is the arrow up. And now down arrow is on delay, off delay. All right. Now, I think we're kind of like finished up symbols as much as we're going to work with. And this is just kind of showing us a ladder diagram. You can see how we have one line across here and have second line there, and there it gives us our nice ladder. And this is a momentary push button that's normally closed, right? Mm-hmm. This is a momentary push button that's normally open. This is going to be a coil that's identified as coil M. Here's a light. We didn't talk about the light symbol, but that's a light symbol with the little dash lines out there. So there's no standard color, but probably R is going to be red. And control wiring is a small wire, so that shows as a small wire. That's control wire. The power conductors are bolder. This shows a wire connection. We're making a connection here, making a connection there. There's a connection made there, another connection there, another connection there, a connection there and there. The numbers, terminals 1, 2, 3, 4, they might just be used for convenience. We got the pilot light. We got, fuses. We didn't show the symbol of a fuse, but that's a symbol of a fuse. We discussed it previously. And, okay, contacts. Here, since we're showing this, as Dennis mentioned, in a de-energized condition, these contacts are open, so they're normally open contacts, and these contacts are closed, which means they're normally closed. And I'm not going to talk about how this circuit operates at this given time. Yes, Steve?
We had some discussions among us off the video about the numbering. And this is a real standard type numbering you'll see where there's multiple contacts controlled by that M coil, and we number them M1, M2, and so on. But when you get a real complicated diagram where you have multiple motors, your starters are numbered maybe M1, M2, M3, and then the contacts might be an M1A, M1B, and so on. So just the student should be aware that your numbering is not a universal thing, that can vary with the situation, with the blueprint you're working with. You just have to really stay within the context of what the manufacturer or the engineer give you.
Well, you do run out of 1, 2, and 3, and 4
Yeah.
pretty quick. You know?
Yeah.
Once you use it once. Okay, well, 1, 2, and 3 are being used. Okay, motor, now motor 2,
Yeah.
we need to start coming up with some numbers. And then
Yeah.
the A, maybe capital A, maybe a lowercase a, you start doing ways of breaking this thing down. All right, that is the end of chapter 1. We are now beginning chapter 2. Let's see what this is talking about. Basic concepts, components, schematics of motor control circuits. Unit 4, components of control circuit schematics. To work on motor controls properly, you must become familiar with motor control schematics and diagrams. Now we've talked about what a ladder, what a wiring, pictorial, now symbols. Now we're going to start putting it together. Let's take a look at a simple control circuit. Using a ladder diagram, we have line 1 connection going to a single pole, single throw switch, going into another symbol called overloads, which we haven't discussed yet, but it's a normally closed contact either way, going physically to a motor, going to the neutral. So this motor is actually operating at line voltage. This is not a control circuit, so probably, I guess we can leave that wire. I'm not sure. Should this wire be a bolder line, you think, or should it be a narrow line here? Because we're not using control. It's a control, but we're using line.
We're switching the power.
We're switching.
Switching the power.
We're
That's a
switching the
manual
power.
motor starter of sorts, so you would probably want the bigger line.
Yeah, I think we're going to go with the bigger line on that one there. Not the big deal for now. Okay, now let's see pictorially, what does that mean? Well, your single pole, single throw switch is your toggle switch here. The overloads, which we'll talk about another time, not right now, is contained in this actual manual motor switch with an overload. And then here's the pictorial of that motor, and then it connects over to the neutral. So here's your ladder diagram of what pictorially is being displayed down here. Okay, Steve, you got a...
I've got a little manual motor starter switch here. One it shows it's how it comes in the enclosure if you buy that whole enclosure. And then here on the other side is just the switch outside the enclosure, and you can see the overloads right here, the heater.
Turn it sideways. I want to see what the side... show me where the line 1 comes in. Where's the line 1 come in? Where's the hot wire come in?
Get my eyes on this. The hot wire on this one looks like it would come in up here, and then the load side comes out down here.
Okay, so it actually is
feed through
going...
that overload.
It's a little different than what we'll show on the graphic here. We'll change that. So it really is... Right now, yours is coming in here.
Yeah, and
it
different
somehow-
manufacturers could lay that out differently too. But
Okay. And so that would be an example of a heater on the side, overload,
over here.
right there in that graphic. And that is what is demonstrating here. And that is a symbol for an overload, which we haven't discussed yet, but now's a good time to pick it up. And I'd love to talk about what the overload does, but I'm not going to do that right now. We're just going to try to show you a simple control circuit. All right, let's see how this thing operates. Single pole switch, there's an overload. The overload is normally closed. We're supplying power conductors, so we'll have all these conductors, the standard size. And over here, I close that switch. We'll then power... Oh, 1 second. The neutral's connected to this side of the motor. The hot wire stops over here. Close the switch. Power continues to the motor. Motor operates. If for some reason the overload operated, and Steve, show them where that overload is, and we'll have Gary zoom in on that, right on the side there, that if for some reason over time something happened that caused, is that like a bimetal that it opens, Steve, if it gets kind of warm? Is that, you think?
This one's a melting pot alloy, a eutectic alloy.
Okay, so it melts some metal?
It melts the solder. There's a, I don't know, I doubt if you can zoom in on
We'll
this.
talk about those.
Yeah.
Whatever it is, it opens that circuit.
Right.
There.
It uses the heat principle. It just heats up some solder, and that solder is currently holding the contacts closed because it's keeping a wheel from pivoting. There's a spring-loaded wheel.
Okay.
And when that solder melts, it just simply allows that wheel to move. The shaft will the shaft is embedded in the solder.
Is there a reset button on that?
Yes. Well,
Or is it automatically, I
No,
guess,
no,
closes
this one-
as it cools down, it just kind of resets itself?
yeah. This I don't see where the reset is on the manual one because it's the same principle. It's going to have to cool down, and you're going to have to
switch.
Yeah. Oh, yeah. On this one, it's probably a switching mechanism when you turn it off, just like resetting a circuit breaker.
Ah, good point.
There's a
Internally.
mechanical
Now,
link in
does
there.
it have
that
an
I can't see.
ampere and a voltage rating on that switch?
This one is 1 horsepower. They're horsepower rated, and it's 115 through 277.
Okay, so it's a 1 horsepower motor rated switch with an overload. That if it heats up, then the overload is already set normally closed, but if that motor was drawing more than the ampere rating of that switch, then that that overload would open and protect the motor from failure. All right, adding an automatic control device. Start reading some of these schematics. All right, so we have our switch and we had our overload, our manual switch we had right here. And we decided we want to add a float switch. So I could turn this thing on but I only want the motor to run under the condition, in this case, using the normally open float switch. I only want the motor to kick in the event that the liquids rose up to a certain level. This would be very common as a float switch, a sump pump assembly in a basement. Steve, you live in Oregon area, or is it Oregon? I know these guys in Oregon are very sensitive how I say Oregon. I've gotten that before. Am I right about it? It's Oregon? Oh, that doesn't matter.
It's
then.
either way, Oregon, Oregon.
Okay. All right. Wherever you're at, do you have a basement in your home?
I don't, but a lot. It's very common, and yes, that's.
Anybody here have a basement? Steve, you got a basement? Now, isn't it flooding right now in North Dakota? You live in South Dakota?
I'm in South Dakota, so we're not flooding, but I have a basement that is in an area with soil conditions where it is apt to, and I have 3 sump pumps.
You have 3 sump pumps. Wow. Okay. Do you have the kind of float switch that we're showing here? What does your float switch look like?
I have a couple of different ones, but one is very similar to that. It's integral to the pump. This is just showing the switch mechanism separate. It's integral to the pump, though.
Oh, so the pump itself would
It's
be
a
sitting in there.
submersible pump. You drop it down in there.
You know what? That's just like my boat. I have a boat, right? I have an automatic pump that when the whatever you call it inside the boat fills up.
Pit.
Bilge.
Bilge in a boat, huh?
But okay, oh, it's a bilge. That's why they called it a bilge pump. I didn't know that. Okay, so anyways, in my bilge, when the water level comes up, it raises the float and it turns on the motor. So that sump pump float is actually built within the motor assembly. Take us a couple pictures of the different ones and send them to Mike, and then maybe we can add it to the book. All right. Any other comments on?
And again, there has to be a differential on those kind of mechanisms too.
Why would you have a
that
different?
so that the pump won't be running continuously.
What do you mean by differential? Because if it goes
So
up,
when
it turns
your
it
float
on.
has to go up to turn it on, and then you don't want it to turn on again. I'm sorry, it has
Oh,
to
I see what you're saying.
go down to shut it off, and then as soon as the first cup full of water comes in, you don't want it to turn on and
You
off
don't want it to
right
be
away.
taking out. All right, it goes on, it starts pumping it, and then it stops. When it stops, it then takes a little bit of water that was still in the hose
Yeah.
back down, just enough to cause it to go
And
back
you don't
up
want that
again,
to
and then
happen.
be going back and forth and back and forth.
Yeah, so you've got a level. You want it to come up to a certain level before it turns on, and then when it pumps out, it'll go below that level to shut off.
Got it.
Your graphic actually shows those little set collars, and you can set those to actually change the function of that.
Aha. I knew that. All right, next one. Let's take a look about adding this control device, this automatic control device, to our existing circuit. Single pole switch, normally open. Overloads, contacts are closed. Float switch is normally open. Motor is not running. I decide I want this thing to work. I close my switch. Overloads are not open. There's no water. Power stops at this location here. There's a neutral on both sides, and the motor's connected with the neutral. Nothing happens. Time goes by, whatever reason, moisture, liquids enter, closes the float switch. Since my single pole, single throw switch is closed, overloads are closed. We now close the contacts for the float switch. Motor kicks on. Hey, guys, we're reading control circuits now. Pretty cool, huh? Ladder diagrams. All right, let's take a look at the pictorial of this. Here is a single pole switch, single throw. Power goes over to, we don't see it here, but power goes over to a set of contacts. I see what it is. Okay, power comes in. So this is just a switch in series with this switch. That if this switch is closed and it goes down, and if this switch is closed, then power comes back up to the switch leg, using electrician's term, and then of course the neutral is directly to the motor. Am I right, guys? So now, because it's series for the current to flow, both switches would have to be closed for us to be able to have this. We have 2 conditions. One condition is you got to turn on the switch. Second condition is the float has to be activated to close the contact. If the float is active to close the contact, but the switch is off, since the switches are in series, nothing happens. Eric?
And the third condition is the overloads have to be closed.
And the third, okay, because we have the switch, then we go to the overloads in series, then we go down to the contacts to sense whether the liquid has risen to a level, then we go to the motor. You know, and if something doesn't work right, by having the concept of like, well, all right, well, what's the voltage between the case and the line side of that switch? It should be what? Using, let's say it's a 120 volt circuit. If we were going to troubleshoot it, if it wasn't working, let's go to troubleshooting now. Well, voltmeter from the equipment case to the line side of the switch would be 120.
volt,
If I turn the switch off, the voltmeter here should be
0.
0. If I turn the switch on, it should be
120.
120. All right, so we got the 120. We know the switch is good. I then take the cover off of the float switch. Voltage is 120 here. The black wire terminating on one terminal. I just double check that. That should be 120. Turn the switch on or off. Okay, got that. Then go to the load side. It should be 0 if the contact is open. Then just kind of put my hand there. Is that right? Just kind of move this guy up and down to find out, okay, well, am I getting 120 on that contact? Yes, I am. Okay, well, then I come along here, then get over to this motor lead, and then make sure the switch is on. Make sure the voltage here, which means the overloads are good. Make sure the voltage is on the line coming in, the load going out, that's good. Come over to the motor, take the cover off, make sure it's 120. Hey, got 120? In my personal opinion as an electrician, I'm done. Goodbye. See you later. You got your voltage. Call somebody to replace your motor. You know, but you got the power there. So you can see how we're slowly building. And let's take a look back here. Here is the ladder diagram of that, right there, what we just did. So we're putting it together. I like this. Anybody have a comment on that before I move on?
Just as a note,
Yeah?
the way you describe that, your switch has to be on and the float has to be made and the relay. Anytime you use the word and, it's basically going to signify that those devices are in series.
And is in series, and I guess you're going to tell me, or
Would be in parallel.
will be in parallel. I like
And
that.
that you keep that in the back of your head while you're writing out these relay ladder diagrams.
So you're saying to